So we have been talking about periodic trends, and we talked about the change in size as we go across the periodic table. Make that a little easier to see. Maybe not so much. Okay, so the last thing that I mentioned was the lanthanoid contraction. So this is the idea that if we look at the transition metals, we expect the trend of going down groups to be continuous, but what we see is between the second and the third row, there really isn't a whole lot of change. And so you can kind of see that if you just pick any random element, one is about the same size as the one below it. So silver is 144, gold is 144. What does that tell us about the densities?
Kind of if they're dense in the middle, or really dense.
Well, all atoms are really dense in the middle, but how can I? You are not wrong.
I love being right in the morning.
How can we compare the densities of the second row and the third row?
They should be similar.
Okay, so they have similar size. So one weighs 107 and the other weighs 196. And so therefore they have the same densities. Does that seem right?
No, that's not.
No, that is not accurate. Okay, so.
So then as you go down, then more dense.
Yes, there's a huge change in density because the size doesn't change. But in that case, we almost doubled the mass, going from 107 to almost 200. So the third row is very, very dense. So our densest elements are actually right in the middle of that row. Osmium, rhenium, and tungsten are super, super dense elements. And let's see if I can actually see their sizes. Yeah, osmium is the smallest in size. So, yeah, that's where we get that. Okay. So one of the reasons that we say this is the case is because if we look at the elements in the third row, they are immediately preceded by the lanthanoids. Actually, this contains both of the reasons. So if we think about the trend continuing going across of getting smaller and smaller and smaller, we've got 14 elements worth of it decreasing. As we can see here, the trend of getting smaller going across isn't exactly steady within the transition elements, and that's true of the lanthanoids as well. So osmium being the smallest in the middle doesn't really hold to that trend. So that's not an entirely satisfying explanation. The reason that they're not a steady decrease, though, leads us to the other explanation, and that has to do with the shielding. So we know that s electrons spend more of their time closer to the nucleus compared to the other elements, right? Because they don't have any nodes that go through the middle. The d electrons have 2 nodes that go through the middle, so we say they are more diffuse, and being more diffuse, that means they're not very good at shielding. So if we extrapolate that out to the f electrons, instead of having 2 nodes, how many nodes do they have? 3. Okay, their L value is 3, so increasing the L value increases the nodes. And because of that, they're even more diffuse. Okay. The other thing that we see is that the size, the extent to which the atoms go outward is more reliant on the principal quantum number, the n. So whether it is a 6 or a 5 or a 4. Well, in that third row, that is row 6 on the periodic table. But what n value do we have for D? Do we have a 6 there? We have a 5. And the F that comes before that is actually a 4. So the extent of the orbitals that we're looking at is not very far. So let's take a look at that on whiteboard here. So if I am looking at, and I'm just, kind of hand drawing this, but I looked up the 4s and the 3d. And so for the 3D, the peak density was, or the highest value of psi was at an R of right around 1 angstrom. Angstrom is a capital A with a little deflector. Okay, and that is for the 3D. For the 4S, it is right around, I want to say, 2.5 or 3 angstroms. Okay, so if we have, this isn't running very dark, if we have this as our 4S, the 3D is kind of like this. It's a lot more narrow. Yeah.
And what does the R mean again?
Distance, radius. Think of it as radius. Yeah. Okay, so this is one of the reasons we can think about losing those s electrons first. It's like, you know, you're driving along the highway, you stick your hand out the window, feel the breeze, and then suddenly, like, you go past the bridge and whack, your hand comes off, right? Because it's sticking out further, okay? So, you know, I'm always very nervous when my kids stick their hands out the window. Yeah.
Can you please get a darker marker?
Yes. The ones that have red in them tend to be harder to erase, but yeah. And I don't know how much darker that is. Let's try.
I have this one that smells fresh.
I'm afraid of the pinks. I really, oh, wait. No, that's the blue one I just got rid of.
Here's some, here's a green one.
I have a brown one. Let's try brown. Oh, you have, oh yeah, the black one. I remember I hid those. That's right. Oh, I hid them so that people wouldn't come in and
Isn't
steal
there?
them.
No.
That's why I put the periodic tables in there. Okay, all right, so this is our 4S, okay? So there's a big difference in size, okay? So when we're thinking about shielding for this 4S here, we don't get a lot of shielding in here because there's the nodes in there, but then these aren't extending out very far, so they can't bond very much. Okay, so we have that going on. So what about our third row transition back? Period 6. Okay, so these two are not relative to each other because I don't want to draw a circle as big as the board. If this is our 6S, and then we have, I didn't look up the sizes of these, I should. That's our 5D, then our 4F, oh gosh, what did it have? Just got, it's like a carnation, all over the place. Okay. So it's got lots of nodes in there, and it is not shielding the size very well. So if I'm looking at hafnium, let's say that's our first real third row there. Hafnium has 72 protons. The shielding on this 6 is very, very small. Okay, and so that's going to pull it in. Okay, then we have one more thing on there that says relativistic effects. So if we think about the theory of relativity, the idea is that Newtonian mechanics, the stuff that Newton was able to describe, force equals mass times acceleration, that all works very well as long as things are big and slow. Relativistic effects apply when things are small or fast, okay? When we approach C, what is C? Speed of light.
You said small or fast or small?
Probably or. But we're not small enough yet to get quite into that area where or alone is enough. So the speed is more important. We're going to focus on the speed. Okay, so for the speed of light, and let me turn the light back on here. If we think of this electron, now it doesn't always go in an orbit, it's going all over the place, it's a wave function, but if we think of this electron as moving, if it's trying to get around this atom, the further out it is, the faster it has to go in order to like keep moving around the atom, right? Okay, so larger s orbitals cause the electron to move faster to what we call relativistic speeds, near the speed of light. So what happens when we get near the speed of light? That's when we get an increase in mass. The speed causes the electron to gain mass. To mass. Okay, let's try this again. Electron gains mass. Not by adding actual matter, but the fact that it is moving fast means that it weighs more. Okay, so that's the whole Einsteinian relativistic effects.
Is that just the way it is, or is there
That's
like-
just the way it is.
Okay.
If you want details, you can talk to Professor Granlund or Dr. Dickinson, but this is as much as I can give you. Okay, it's going to gain mass. As it gains mass, then that means that it is, because it's heavier, it gets contracted towards the nucleus. Okay, so you can kind of think of this as the mass of the object and gravity of pulling those things together. It's like being pulled in because it is more massive. Okay, so instead of the 6s being way out here, instead it gets pulled in and we have a smaller distance that it travels. So generally, chemists will just say the reason that that happens is because of relativistic effects, period. End of statement, moving on. But the idea behind it is that those electrons in these 6s, 7s, 8s orbitals are moving very, very fast. They gain mass, and that causes them to be pulled in. That also means that as we move across the, or as we move down the periodic table, it becomes more difficult to remove yes electrons because they're being pulled in, right? Okay, so if I'm going to go back one slide. If we look at boron, so right after the section break, but at the top, boron will take on an oxidation number of 3. Usually doesn't form an ion, but an oxidation number of 3. That's pretty common for it. Aluminum, almost always 3, pretty much doesn't do anything else. Gallium is pretty rare, 3 is pretty common, but as we move down, once we get into, what's by low gallium? Is that indium? Let me look over here. Indium. Once we get down to indium, then it is more common for the +1. Why do we have those particular charges? Those have valence electrons, their highest end level of 2 s's and 1 p. And so when we're looking at boron and aluminum, they lose all 3 of them. But once we get down to indium, it can lose all 3, but it also can just lose 1 and be okay. And then once we get down to thallium, pretty much never loses those. So those relativistic effects are making it so that those s electrons really don't come off. So we call this the inert pair effect. The inert pair effect is the idea that because the s electrons gain mass, it becomes more difficult to remove them once we approach relativistic speeds. So for the inert pair effect, for heavier elements, we see the inert pair effect of it being difficult to remove the s electrons. And so it's not like there's a breaking line where it occurs and it doesn't occur. It is more common further down, but you will definitely see it in row 6 and beyond. So usually in row 5, these you'll see both removing the s electrons and removing the p electrons and removing both of them. But in the 6th row, almost always the lower oxidation state is preferred. Strong. Okay. So that ties together a lanthanide contraction along with this inert pair effect. Now we are going to move on to ionization energy. And this should be something that we have seen before. Okay, so ionization energy is the idea of how much energy does it take to pull an electron away. Okay, so going from a neutral sodium atom to pulling that electron away. Now, something that we have to remember is that this kind of thing never happens in isolation. So we also have to think about the idea that electron is going to be going somewhere. There's usually something that is doing the pulling. So while it requires energy, we have to put energy into the sodium in order for this to happen, which would not be favored. Using energy usually isn't favored. We gain energy by adding that electron somewhere else. So it's almost always favorable to add an electron to a neutral atom. So it's super easy to ionize sodium. And here I'm going to darken the screen again so we can kind of see those elements. So you can see as we go across the bottom, that's Z. What is Z? Nuclear charge, which tells us what about the atom? Where does it get its charge from? Where does the nucleus get its charge from? Protons. Okay, so this is number of protons. So Z is also protons, which is also the atomic number. Okay, so basically we're just going in order of the elements across the bottom. Okay, so as we go across, we don't see this nice straight line going upwards. It goes upwards and then it drops. It goes upwards and then it drops. It goes upwards and it drops. Okay, so the peaks that are highlighted there, helium, neon, argon, krypton, xenon, and radium, what can we say about those? Those are the noble gases. So within each row, the highest ionization energy is the noble gas. So if we think about what that means it is the most difficult to remove an electron from a noble gas, right? Okay, so we already knew noble gases don't like to lose their electrons, so that makes sense. We also know the noble gases are the smallest ones in the group, right? And so it makes sense that those electrons are very close to the nucleus and it's very hard to pull the electron away. The easiest ones to remove are the ones that are in the yellow at the bottom. So we see lithium, sodium, potassium, rubidium, and cesium. And those are the first ones in the row, which we also know form a +1 charge, easy to pull off an electron. And we know that they're the largest. Okay, so there's this opposite trend between ionization energy and to remind me not give you enough time on the quiz. Okay, opposite trend between ionization energy and radius. So I'm quickly going to go through these things. if we compare ionization energy and electron affinity is the opposite. This is the gaining the electron. So I said taking an electron away doesn't happen in isolation. Something has to be taking the electron. So when we have electron affinity, we are going to have, and some books reverse them, some of them don't, but we have a favorable electron affinity when we have a high ionization energy. So you can see chlorine has a high favorable electron affinity. So that bottom one is the electron affinity. Let me advance this one as well. But what about argon? So argon is going in the opposite direction. It's very high for ionization energy, and on here it's very low for its electron affinity. The reason for that is argon is a noble gas. And in order to add an electron, would we be adding the electron to the same valence level? So argon has 3s2, 3p6. The next electron is going to go in the next level. It's going to go into the fourth level. So it is not favorable to add it to the noble gases. So generally the trend is when it's easy to remove an electron, it's hard to add an electron. When it's hard to add an or when it's hard to remove an electron, it's easy to add an electron, except the noble gases don't want it. Okay. I really prefer when they inverse the sign of the electron affinity because adding should be easier. So it's actually negative. So some books write it as the energy negative of adding an electron, and some write it as positive. And so this book doesn't do it the way I like it, but the trend stays. Okay. So we're going to stop there. And do you have any questions about quiz stuff? Yes. So isoelectronic would be the same number of electrons, but if we think about from your homework where we were looking at titanium with 22 electrons and chromium 2+, which also has 22 electrons, we wouldn't necessarily consider those isoelectronic because they don't have the same configuration. So when they're isoelectronic, not only do they have the same number of electrons, they're in the same orbitals as well. Okay. Any other questions? Now, to be fair, on your quiz, I can't remember if I asked that question, but if I did not get that nitpicky. So I was not trying to trick you on that question. Okay, so I'm going to pass this out. You may use your notes on this, so you can leave your notes out.